So I would like to be with you in Paris, but anyway, it's nice that I can give this talk, this online talk. So for convenience, in this talk, I will take the example of the adaptation of a pathogen population, but you will see that the mathematical framework can be adapted to many other situations. Let me begin with a simple mathematical model describing the adaptation of a pathogen population on a unique host. So the model is the following one. U is population density at time t, and X corresponds to the phenotype in the population. So by phenotype, I mean a vector in Rn, and by phenotype, in fact, we mean the heritable part of the whole phenotype. So the equations that governs the density U of t and X is the following one. So there is a mutation term here, which is described by a Laplace diffusion operator, a growth term, which can be interpreted as fitness, and a non-local competition term. So contrary to, for instance, KPP equation, where competition is at a given position, here, all the individuals are in competition, whatever their phenotype. So the typical assumption when there is a unique host is that there is a unique phenotype optimum. So this means that, for instance, R of X can be of the following form, with some R max corresponding to the maximum growth rate when the phenotype is optimal. Alpha corresponds to the intensity of selection, and capital O here corresponds to the phenotype optimum in the given host. So this type of model can be used, for instance, to understand phenomena such as antibiotic, the occurrence of antibiotic resistance in bacteria. There have been many mathematical studies on this type of models with, for instance, unique optimum like here. There's the work of Alfaro, Rémi Carles, and also Alfaro and Verruete. Other works with Hamilton-Jacobi approach by Pertam, Barr, Lorz, Miraimi, and their collaborators. There are also several works in the case of unique moving optimum, but my talk will not be about this case of a moving optimum here. We assume that the optimum do not move with time. But instead of this, we focus on the case where there are several hosts. So I begin with the case of two hosts. So we assume, again, a population of pathogen, which try to adapt on two different hosts. The mathematical model is the following one here. The equation on each host is almost the same as in the case of a unique host, with a growth term here, which depends on the host. So the growth term, we assume again that there is a unique optimum on each host. So globally, there are two optima, O1 and O2. O1 corresponds to the phenotype optimum in the host number 1, and O2 corresponds to the phenotype optimum in the host number 2. So you see that on each host, you have the same equation and as in the case of a unique host, plus a migration term. So this migration term here simply means that individuals move from the host 1 to the host 2 at a rate delta, and similarly from host 2 to host 1. So we assume symmetric dispersal. The underlying biological questions that we can treat with this kind of model is to understand, for instance, spillover or host jump in viruses, and for instance, the emergence of zoonotic disease. So there are many cases of zoonotic disease. Of course, there is influenza A, where the animal reservoir is correspond to aquatic birds, and several types of coronaviruses, for instance, MERS and SARS-CoV-1 and SARS-CoV-2. Another type of questions that can be studied with this type of model is to understand the resilience of agroecological systems with where several cultivated varieties are mixed compared to standard agricultural systems with a single variety. So the question will be to understand if from the point of view of the pathogen, this case is more suitable than this case or not. Again, there are several mathematical studies. and also theoretical biological studies, such as the first one here, where the author focused on, with formal mathematical arguments, on the occurrence of specialist versus generalist strategies. So by specialist strategy, we mean that there are, in fact, two different populations. The population on the host number 1 and the population on the host number 2 are very different, in the sense that the one on the host number 1 is really adapted to the first host. This is the dark gray one here, and which is okay, slightly adapted to the second one, but not very much. And the population on the second host is well adapted to the second host and not to the first one. And by generalist strategies, we mean that the two populations are very similar. So mathematical works on this type of problems, and which were based on constrained Hamilton-Jacobi approaches, shown the existence of a threshold for the migration rate, such that when the migration rate is small, there are two specialist populations, like in this case here. And when the migration rate is large, there is a unique generalist population. And there are also some works by Leonard Dickens that presented his works this morning, but on sexually reproducing population, which is not the case that I consider here, with only asexual populations, such as bacteria or viruses. And there are also some works on persistence and extinction based on a spectral argument, and I will say a few words about this work in the next slides. But here, I would like to focus rather on the case with more than two hosts. So the general model is the following one. So you see the same form as in the case of a unique host for the first part here, with a growth term or a fitness term, which depends on the phenotype and on the host, with a unique, each time on each host, there is a unique optimum, which is denoted by OI here. And there is this migration term between the different hosts in the system. So this migration term means that each host sends migrants with a rate delta. So this term corresponds to the fact that migrants move to other hosts with a rate delta. And then these migrants are shared into the k-1 other host in equal parts. This is why there is this other term here. Okay, so from a schematic point of view, you have this kind of dispersal. So each host sends delta over k-1, sends migrants with a rate delta over k-1 to each other host. So this corresponds to a symmetry assumption again. But here, this is symmetric in terms of dispersal, but there is a possible asymmetric structure in the system due to an asymmetric structure of the phenotype space, because it will depend on the respective position of the phenotype optima. They can be symmetric. For instance, we can have an equilateral triangle, but in general, this structure is not symmetric. So the underlying biological question, again, are related to the understanding of spillover or host jump in viruses, but here in the presence of intermediate hosts. So in the case of 3 hosts, it will be 1 intermediate host. In the pathogens that I mentioned in my previous slide, in fact, in each case, we suspect that there is an intermediate host. For instance, in influenza A, this could be pigs or other species or some bird species, the intermediate host between the animal, the aquatic birds, the animal reservoir, and the human beings. In MERS coronavirus, the intermediate host between the bats, so the reservoir, and the human is probably camels. In SARS-CoV-1, probably CIV, and in SARS-CoV-2, we don't know yet. So the question that I would like to deal with here is, does adding a third host always increase or always decrease the chances of persistence of the pathogen in the global system? And in the particular case when there are 3 hosts, which position of the phenotype optimum corresponding to the third host lead to higher or reduced chances of persistence for the pathogen. So I would like to compare this situation with 2 hosts with different optima, with this situation with 3 hosts with different optima, with other situation where the position of the third optimum is different. So I will first recall classical results in the case of 1 and 2 hosts. So in the case of a unique host, so there is no dispersal term here. So this is this standard equation. So here, existence and uniqueness can be easily obtained from the linear equation. Indeed, let's consider this the solution U tilde of this linear problem for which it is well known that there is a unique solution. And let's see how we can construct the solution of this problem from the solution of this one, and conversely. Let's set R bar as the mean growth rate in the population, which is described by this equation. Okay, so this is defined as this. This is simply the mean growth rate in the population. And let n of t and n tilde of t be the solutions of these 2 ODEs. So the first one is a logistic ODE with a growth rate R bar, and the second one is a Malthusian ODE with a growth term R bar. In fact, the solution of the non-local problem here is simply equal to n of t over n tilde over t times U tilde. So this, in fact, this can be understood by saying that for these 2 models, the phenotype distribution is the same. So you only have to multiply by the population size to get the solution. So this is proved in, for instance, in our paper with Florian Lavigne, François Hamel, and Guillaume Martin. And in this case, persistence occurs if and only if we have the following inequality between the maximum growth rate, so the mutation terms, the dimension of the phenotype space, and the selection term. And in fact, using the results of Alfaro and Verwete, we can see that this property is equivalent to the negativity of the principal eigenvalue of the following Schrödinger operator with confining potential. In this case, if we recall that R of X is the following form, the principal eigenpair can be computed explicitly. And in fact, lambda 1 corresponds to the term which appears here with a minus sign. And the principal eigenfunction can be computed also explicitly, it's simply a Gaussian. Let's move to the case with 2 hosts. So I recall the equations that I've mentioned at the beginning of my talk. So here, without loss of generality, we can assume that the 2 optima are on the first axis. So the first one is at the position minus beta 0, 0, 0. And the second one at the position beta 0, 0, 0. So they are symmetric with respect to the origin. For simplicity, here I assume also that the initial condition is symmetric with respect to the origin in the following sense. So U naught of x is equal to U naught of iota of x with iota as the following transformation. In this case, we can prove existence and uniqueness of the solution of the Cauchy problem. And again, the proof is quite simple to obtain based on a comparison with the linear problem. So in the linear problem, we remove this non-local term and this non-local term. And then again, we can see that the solution of the non-local non-linear problem can be obtained simply by multiplying the solution of the linear problem by a ratio between solutions of ODEs. So to describe the persistence and extinction results, we define a principal eigenvalue lambda 2 satisfying the following problem. So this is a standard problem with Schrödinger-like operator here, plus this term which describes migration between the 2 hosts. Here, lambda 2, as I said, is the principal eigenvalue. So the index 2 corresponds to the number of hosts. This is not the second eigenvalue. And you see that the couple of eigenfunctions correspond to positive eigenfunctions. So in this case, we have the following persistence and extinction results. In fact, sufficient and necessary and sufficient condition for persistence is that lambda 2 is strictly negative, so the instability of the steady state is 0. In the following sense, so the total population in the system, so the total population in host 1 and plus the total plus the population in host 2, satisfies the following properties. So it ever there is a sequence of times converging to infinity and infinite seconds, such that at all these times the population is larger than minus lambda 2, which is strictly negative. So this means that there is persistence. And in the other case, when lambda 2 is non-negative, then for any compactly supported initial condition, the population is driven to extinction at large times. So there is a criterion based on the sign of the principal eigenvalue. So we can use this criterion to understand the behavior of the system when we change the parameters. So for instance, let's see what happens when we change the migration rate between the two hosts. So first, we can see that the map lambda 2 of delta is increasing. So which means that increasing migration leads to lower chances of persistence. And in particular, when the migration rate converges to 0, lambda 2 converges to lambda 1. So it means that each host, in fact, behave at if it was isolated without migration. It's the same. Okay, it happens as if it was as if there was a unique host. When the migration rate converges to infinity, on the contrary, lambda 2 converges to some quantity lambda 2 infinity, which is the principal eigenvalue of a scalar operator where the growth rate is replaced by the average value between the growth rates on the two hosts, in the two environments. So this is a kind of homogenization result, in fact, because there is a very high migration for the species. They jump continuously from one host to the other one. And also this means that the population is like a generalist population, as in the results that I presented at the beginning of my talk. So in particular, we see that lambda 2 is always strictly larger than lambda 1. So this means that the presence of the second host has a negative impact on the pathogen. And in fact, this effect is increased when the migration rate, the mutation coefficient, and the distance between the two optima are increased. So let's move to maybe the more interesting part of the most interesting part of this talk, the case with more than two hosts. So I recall that the system that we consider is the following one. So again, we can prove existence and uniqueness of the Cauchy problem, but here this is slightly different. We cannot use the comparison with the linear problem. We cannot construct the solution based on the solution of a linear problem because here symmetry is breaked in this case, because in general, since the hosts do not respect any symmetry assumption, the position of the optima of the different hosts, the population sizes in the different hosts could be different. And therefore, we did not manage to construct the solution of this problem from the solution of a linear problem, and we don't think that this is possible. So we have to use a fixed point argument. Again, for this system, we can prove persistence and extinction results based on the sign of a principal eigenvalue. So the principal eigenvalue is defined in the same way as in the case with two hosts. So it is defined as follows. So this is the unique. There is a unique principal eigenvalue on the unique set of principal eigenfunctions up to multiplication, which satisfies the following system with positive principal eigenfunctions. And the results are the same as in the case with two hosts, which is that persistence occurs if lambda k, so the principal eigenvalue associated with k host, is negative, and extinction occurs when this quantity is positive. So extinction is quite classical because we simply have to compare with multiples of the principal eigenfunctions multiplied by an exponential of the principal eigenvalue times t. And based on the sign of this eigenvalue, we can easily prove that at least when the initial condition is compactly supported, the solution will converge to 0. Persistence is maybe less classical, so I can show you the sketch of the proof. So assume that the principal eigenvalue is negative, and assume by contradiction that the total population remains below some value epsilon at large time, so for all t larger than some t capital T. Then each subpopulation Ni is below epsilon, since the total population is below epsilon. And all of them, of course, are positive. And consider the solution of ui epsilon of this linear problem. So in this linear problem, I have replaced the integral A here, which corresponds to the population Ni, the total population Ni on host number I. I replaced it by epsilon. And I take as initial condition ui of t. Then, since we have assumed that Ni was below epsilon, so this quantity is smaller than epsilon, so a comparison principle, but applied to the linear problem here, implies that ui is always larger than ui epsilon. And then, of course, n of t is larger than n epsilon of t for all time t larger than capital T. And then we apply another comparison principle to the same problem here to compare the solution with the principal eigenfunctions multiplied by an exponential of minus lambda minus epsilon t, multiplied by some constant to put it below the initial condition here. So here you can see that there is a R, which means that in fact this is not exactly the principal eigenfunction, but this is the principal eigenfunction computed with directly boundary condition on a ball of with radius R, which converge to the principal eigenfunction. But we do this in order to be able to put it below the initial condition here. Anyway. This proves that for any epsilon between 0 and minus lambda h, this quantity will be positive, and therefore Ni epsilon will converge to infinity for the linear problem, which leads to a contradiction because Ni is supposed to be below epsilon. So finally, this proves that there is persistence and that at some time the solution will be larger than minus lambda h. Now, again, since we have this criterion, we can use it to understand the behavior of persistence and extinction behavior of the solution depending on the parameters. So we have a result which is quite similar to the case k equal to 2 in the case where k is larger than 2. So again, when there is no migration between the host, of course, lambda k converge to lambda 1. When migration is very large, lambda k converge to the principal eigenvalue of this operator, where again, this scalar operator, where the growth term corresponds to the average value of all the growth terms between the different hosts. And in fact, we can compute explicitly the principal eigenvalue, this limit principal eigenvalue here, which correspond to the mean value of the growth terms computed at the center of mass of the system between the different optima. Let's now compare the case with 2 hosts versus the case with 3 hosts. So we would like to see what happens if our 2 initial hosts are fixed. So for instance, here, as before, I assume that O1 is at the following position, O2 is at the following position. And what happens if we add a third host in this system? So we add another host with corresponding to a phenotype optimum O3, and we would like to see whether lambda 3 is larger or smaller than lambda 2. When lambda 3 is smaller than lambda 2, this means that adding a third host increases the chance of persistence of the pathogen. So we define this set capital lambda corresponding to the position which give higher chance of persistence for the pathogen when we add a third host. With something like we call this a springboard effect, because this means that, for instance, if you have two species, I don't know, bats and human beings, and the pathogen cannot jump between the bats and the human beings, so it needs another species to be able to play a role of springboard to be able to jump to the human beings. The difference lambda 2 minus lambda 3 can be interpreted as the fitness gain with 3 hosts compared to 2 hosts. So it can be positive or negative. So this is a numerical simulation of this fitness gain, which so this simulation has been done by Florian Patou. So the position of the first optimum is here, the position of the second optimum is here, and each point corresponds to a different simulation with a third host at the position of the point. So when you are inside the red region and blue region here, this means that the fitness gain is positive. So the pathogen fitness will be higher in the presence of the third host compared to the case with 2 hosts. So we wanted to be able to characterize this region from an analytical point of view. So we began by considering the case of large migration rates. So in the case of very large migration rates, so when delta converges to infinity, the region capital lambda converge to the open ball, which is centered at the origin and with the radius square root of 3/2 beta, which is larger than beta, the distance between O1 and O2 and the origin. So this open ball, the boundary of this open ball is represented here with the black circle. And you see that the 2 initial optima are inside this ball, so which is quite interesting. So this means that if O3 is superimposed with the initial optima, then it's adding a third host is always better in terms of persistence. So for small delta, we don't have the same shape here. In order to characterize what happens when the migration rate is small, we also considered, so we computed the derivative of the principal eigenvalue with respect to the migration rate. So we obtained the following formula. So the proof of this result and of several other results is based on the use of the Rayleigh formula, so classical Rayleigh formula, with here the normalization condition, the following normalization condition. So the integral of the sum of the square of the eigenfunction is equal to 1. And so lambda is realized the infimum of a Rayleigh quotient, where the Rayleigh quotient is the following one. So with a standard part here, which is very standard for Schrödinger-like operators, and this second part corresponding to the migration term with the product of the pairs of the eigenfunctions. And so, using this formula, we were able to compute this derivative, which corresponds to the term which is here. And since when delta is equal to 0, we know that lambda 2 is equal to lambda 3 is equal to lambda 1. We know that the difference between lambda 1 and lambda 2 is equal to 0. We can compute also the value of the derivative because the eigenfunction, we know that the eigenfunction converges to Gaussian in the particular case where R is quadratic. Thus, we can explicitly compute in this case the region, the limit region when capital lambda, when the migration rate converges to 0. And it has interesting properties. So it is characterized by this formula. And it has interesting properties. So for when beta, the distance between the two optima is small. So in fact, here the graphical is not, the picture is not correct because this 2-1, it should not be the same scale. In fact, this 2-1 should be very close. In this case, this is like an athletic stadium. And when the distance between the 2-1 is larger, we obtain something like an oxygen molecule. And this is confirmed by numerical simulation with a small beta and larger beta. We don't have the same shape for the region which adding a third host improves persistence of the pathogen. Another result that we can prove analytically is that when the third optimum is superimposed with an optimum corresponding to one of the first two hosts, then it always also improves persistence. But we can also obtain a situation where adding a third host reduces the chances of persistence, in the sense that here, if we assume that O1, O2, and 3 form an equilateral triangle, then lambda 3 will always be larger than lambda 2, which means that it does not belong to the set that I have defined previously. So let's see how we can prove this result about the equilateral triangle. So consider the equation satisfied, for instance, by phi1. So the equation is the following one, in the case with only 3 hosts. So k minus 1 is equal to 2. Let's multiply this equation by phi1 and integrate by parts. So we obtain the following equation. And then let's observe that the integral of the product phi1, phi3 is equal, in fact, to the integral of the product phi1, phi2, or phi2, phi3, because of the invariance by rotation of the eigenvalue problem and the uniqueness of the solution of the eigenvalue problem. So this is a schematic representation of the 3 eigenfunctions. So we can replace phi3 by phi2 here. We can add these two terms to obtain this equation here. Similarly, we can do the same for phi2. We add these two equations, and finally, we obtain the Rayleigh quotient, but the Rayleigh quotient associated with only 2 hosts. So this means that lambda 3 here is equal to the Rayleigh quotient associated with 2 hosts computed at phi1 over something which is needed for the for the normalization condition. And because lambda 2 realizes the minimum of the Rayleigh quotient Q2, this means that lambda 2 is always smaller than lambda 3 in the case of an equilateral triangle. So let's now look for an optimal position of the third host. So first of all, we can use a projection result. So assume that O1 and O2 are again minus beta 00 and plus beta 000, and assume that O3 is of the following form without loss of generality, A1, A2, 00. And let's consider the projection of O3 on the axis O1, O2. So this means that we would like to compare this situation with this situation. Then we can prove that doing this projection always decreases the principal eigenvalue, which means that this is always better in terms of persistence of the pathogen. This situation is always better than this one. To prove this, we use the notion of Steiner symmetrization of a function. So let's consider a function h, scalar one-dimensional function, for instance. So the Steiner symmetrization is a unique function which is symmetric with respect to x equal to 0, non-increasing in positive value of x, and has the same distribution as the initial function in the following sense. So this means that if you have a function of this type, the Steiner symmetrization has the following form. This simply means that you can cut your function into slices and move the slices to obtain something which is symmetric and decaying from the origin. This idea of Steiner symmetrization can be applied in more than one dimension. So you can apply this sequentially with respect to each variable, but here we will only apply it with respect to one variable. Here, for instance, the second variable. Consider this function. If you apply the Steiner symmetrization with respect to the second variable, you obtain something like this. So this this symmetrization has some properties. So first, it is obvious from the definition that for any measurable function f, the integral of f of h is equal to the integral of f of the symmetrization. Second, we've got the RD Polia inequality, which means that the integral of the product of two symmetrized functions is always larger than the integral of the product of two non-symmetrized functions of the initial function. Third, this is the Polia-Szego inequality. We know that performing the symmetrization reduces the integral of the square norm of the gradient of the function, because it reduces the variation of the function. So let's multiply, come back to the eigenvalue problem, multiply the line I by the eigenvalue phi I, and add all of the lines in the system. We obtain that lambda 3 is equal to the following quantity. We apply the Polia-Szego inequality to this term, the RD Littlewood Polia inequality to this term, and RD Littlewood Polia inequality to these terms. And finally, we check that the symmetrized function is an admissible set of eigenfunction because they satisfy the normalization condition, the following normalization condition. In fact, here we use the fact that R1 and R2 are stable by Steiner symmetrization, and that to obtain the following, the last inequality here, because here this is lambda 3 associated with the initial distribution of the optima. So we see that this is larger than a Rayleigh quotient associated with O1, O2 on the projection of O3, and therefore this is larger than lambda 3 associated with the three following optima, because it realizes the minimum of this Rayleigh quotient. So, and this will be the end of this talk. So what is the optimal position of O3? So I let you try to guess what is this optimal position from this numerical computations. Of course, we would like to say that this is this position, so the host in the middle, which was in the title of my talk. But in fact, what we can prove is that this is not true in general. In fact, when the two hosts O1 and O2 are far from each other, it is always better to put O3 close to one of the two initial hosts compared to putting the third host just between the two initial hosts. So this means that here the origin is not always optimal, and this will be my last slide. The idea of the proof is the following. So let's consider this situation with a host just in the mid-between the host 3. The phenotype optimum corresponding to the host 3 is just between the host 1 and the host 2. And assumes that beta is very large. So everything works as if each host was completely isolated. And in fact, all of the migrants that it sends to the other hosts are lost in some sense, because they are not adapted at all to the host in which they are arriving. So they die in some sense. So this means that this is like if the system had the migration term was simply a lost term without receiving anything. And in practice, we show that in the Rayleigh quotient, the integral of the products between the eigenfunction converge to 0 as the distance between the hosts is converge to infinity, which enables us to prove that lambda 3 converge to lambda 1 plus delta. On the other hand, if we have this configuration where the two hosts O1 and O2 are separated by 2 beta, like here, but with O3, which is very close to O1, then O2 is isolated. So from the point of view of O1 and O3, 1/2 of the migrants are lost. All of the migrants that they receive from O2 are lost, in fact, because they are not adapted. And we can prove in practice that lambda 3 converges to lambda 2 associated with this couple of hosts plus delta over 2. And in particular, if O3 is superimposed with O1, then lambda 3 of O1, O2, and O3 converge to lambda 1 plus delta over 2, which is always smaller than this, which means that persistence is better in this system compared to this system, which proves that the origin is not always optimal. So thank you very much for your attention.
Okay, thank you very much, Lionel, for this very nice talk. So we have a little bit of time for questions. So people in the room may raise their hands, and also online you may either raise your hand or write your questions in the chat.
So let me start. Hi, Lionel. Thank you very much for the very nice question. It's Vincent. Don't know if you can see me. You compare the new player O3 with lambda 2, but lambda 2 was already below lambda 1. What if you compare it with lambda 1? Would it change your conclusions? You are muted. We can't hear you, Lionel.
Yeah, Lionel, you're muted.
I don't know why. Okay, fine. I don't know what happened. In fact, no. Lambda k is always larger than lambda 1 for any k. So yeah, this the comparison is obvious. In fact, okay. Because lambda 2 is larger than lambda 1, which means that persistence is better with only one host compared to two hosts.
Okay.
Yeah, thank you, Lionel, for these talks. It's great. And so my question is a little bit going ahead of this. When you add a host, you increase somehow the possibility to survive. So what happens if you compare the lambda with two hosts at O1 compared to something around an O3 around O1?
So the situation with two hosts but at the same position.
So yeah, what is the difference between the case here where you have O3 close to O1 and the fact that you have two O1?
Okay, so when you have two O1, I think that this corresponds to the case of a unique host, in fact. So having a third host, for instance, in this case, if here O3 was at the same position as O1, okay, you see that lambda 3 will be very close to lambda 1 plus delta over 2. Whereas if you have two O1, you can prove that when you have 201, this is exactly the same as if you have a unique host. So if you have 201 with migration between the 201, in fact, it's like if you have a unique host, so the principal eigenvalue is simply lambda 1. So lambda 3 is always larger than lambda 1 in this case. Because I don't know if it was your question.
Yeah, right.
Yeah. When you have 201, you can see that, in fact, this is exactly as if you had a unique host.
Yeah, thank you, Lionel.
Thank you.
I was curious about your model with time dependence, and if you, by any chance, you can say something about long-time dynamics. If you can, you have candidates for stationary solutions, or
Yeah. In fact, it's very complicated, but it's what. In fact, the study of the stationary state and the convergence to stationary state, we have not done it. We tried, but in fact, this shows that the problem is very rich in the sense that we suspect that the stationary state, in the case with more than two hosts, are not proportional to the principal eigenfunctions. Okay, in the case with a unique host, the stationary state is a principal eigenfunction. In the case with two hosts, this is again proportional to the principal eigenfunction. But with three hosts or more, when there is no symmetry, the population size is not the same. So for instance, here we suspect that the population size in this host, so the integral of U2, is smaller than the population size in the host 1 or in the host 3 because it is disadvantaged compared to the two here, because it receives nothing from the others here. It receives individuals which are not adapted at all. And therefore, the mass of the stationary state of O2 is smaller than the mass of the stationary state associated with O1 and O3. And this is why this is more complicated than usually where the stationary state are simply eigenfunctions. So we can only say this, that this is non-trivial and that the population size are different. And okay, that the eigenfunction are not stationary solution in general.
Thank you. And numerically, did you try to run some tests or even to check if there might be some interesting dynamics like limit cycles or something like that?
No. We focused on the eigenfunctions and on the comparison between lambda 3 and lambda 2. We did not try to see the behavior of the Cauchy problem, in fact.
Okay, thank you.
But yeah, I agree that this would be interesting, but yeah, there are many things to study
you can
about
do so much
values, so maybe it will be for
I see, yeah.
another study.
Okay. Thank you for a very interesting talk anyway.
Thank you very much.